Okay, so thank you very much and welcome everyone to my presentation on the porting effort of CaNS using OpenACC for fast fluid dynamic simulations at scale. And before dwelling into the actual presentation, I need really to thank my colleagues and collaborators at TU Delft, University of Rome Sapienza, my collaborators at NVIDIA, which greatly helped with the porting effort of previous versions of CaNS and also this one. And of course, the excellent community resources, namely the OpenACC Slack channel, but also the NVIDIA developer forums, which were also very, very helpful. So why do we bother to keep pushing the limits of our numerical solvers? I mean, maybe this doesn't need to be motivated for this audience, but of course, in climate and energy, we need to keep increasing the resolution of the systems we are simulating. So we rely lesser and lesser on modeling assumptions that are often questionable and decrease the reliability of our predictions. But also in health applications, we need not only often to simulate large domains, but we need to do it fast. And even for the relatively simple case of turbulent water flowing in a circular pipe at high speeds, there are some questions about the nature of the turbulent flow that remain elusive. And of course, the common denominator in these problems and many others is that we need to solve the Navier-Stokes equations in some form. And that is precisely what CaNS does. CaNS is a fast finite difference incompressible Navier-Stokes solver. You can find the repository over here. And just to give you a bit of a feeling for the code, so it's written in modern Fortran. It has a relatively small source code, so about 15,000 lines of code. And maybe its most distinct feature is that it has a versatile FFT-based Poisson solver for the pressure equation, which imposes mass conservation in a Navier-Stokes solver that, even though uses FFTs, allows for some flexibility with respect to the boundary conditions that it can be accommodated, like not only Fourier transforms, but also sine and cosine transforms. So the first porting effort was actually in 2018, but very recent. So in summer last year, we refactored the code in version 2.0 with a fresh porting using OpenACC and a hardware adaptive domain decomposition library called CUDA, which allow for many GPU parallelization. So the source of CaNS is kept relatively simple, even though some extensions for more complex flows like particle-laden flows, multi-phase flows, or even nowadays urban flows have been extended. These are not in the main solver, but instead we use CaNS as a base Navier-Stokes solver on top of which we add more features. And the reason for this is that, then the main source is more self-contained and more easily maintainable, because CaNS is also often used for introducing new scientists to massively parallel turbulent simulations. Of course, there are other tools, even within the Dutch community, like AFID, MicroHH, and DALES, which have a similar algorithm, but are more focused in some specific applications, like, for instance, atmospheric flows. So just to give you a bit of a feeling of numerical algorithm and workload, so it's a memory-bound type of workload where most of the operations are simply explicit finite difference stencil operations in 3D loops, which are easily parallelized using ghost cells or halo regions. And really the tricky thing in terms of porting difficulty is the FFT-based Poisson solver. So why is that? Well, because the computational complexity of the Poisson solver is similar to a three-dimensional FFT, but with a twist that we do not really necessarily do a 3D FFT, but we maybe do a cosine transform along this direction, a sine transform along that direction, and then we need to solve for a three-diagonal system along the third direction. So to do this, we need to have a domain decomposition that looks like this, where we have the MPI tasks here in colors that need to be first aligned with the in the X direction such that the data to compute the FFT along X is local to each task. And then we sort of need to rotate this domain decomposition to do FFTs along Y, and then to solve with the Thomas algorithm the final system along Z and do the reciprocate operations. And this sounds simple, but actually each of these transposes is an all-to-all operation, which is extremely challenging from a parallelization point of view, especially on GPUs, because we are in a paradigm where we have really huge heterogeneity in terms of cluster node topologies. And nowadays, even GPUs talk with each other in possibly different languages. There's many GPU communication backends. For NVIDIA, we have Nickel and Vishmem, in addition to our, beloved MPI. And at the low level, there's also many possible approaches for implementing these transposes. So which one to pick? And with so many options, how can we be sure that we are exploiting the resources optimally? So fortunately, in parallel to the development of CaNS 2.0, the CUDA NVIDIA library was developed, and it does what it does is really nice. At runtime, this library implements essentially these transpose operations with all possible NVIDIA communication backends and many low-level implementations. And at runtime, it does sort of a runtime auto-tuning step that checks what is the best combination of processor grid and communication backend, so that we can ensure that depending on the system, we are exploiting resources efficiently. And the nice thing about OpenACC is that it interoperates so nicely with CUDA that it was really swift to adopt this library in our code using OpenACC. So this was about CUDA. And so why OpenACC? So this is a bit, of course, my own experience. So I think it has quite some nice advantages. It is simple. The standard is simple. The syntax, in my view, is neat. It's high level. So for someone with a fluid dynamics background like me, it's excellent. Easy to prototype. So if I offload a loop without handling data movement in the most, if I do it in the most vanilla way, under the hood, data movement will be taken care of, and I no need to worry, and I can then leave optimizations for later. Of course, there is a first-class support by the NVIDIA compilers, and performance portability is showing great promise. Great interoperability again, and that's very important for me. That really helped is a thriving community where whenever I have troubles, I know that I can ask really like some experts will be able to help me a lot. Of course, being high level also is a con, because we are sort of left at the mercy of the compiler, and there's different level of maturity in different implementations. So yeah. Now, some guidelines that I follow during the porting. Well, CaNS works in a GPU resident calculation, meaning that so whenever we initialize the calculation before we enter in the main time loop, the whole data is moved to the GPU, and then everything is, the whole calculation is performed on the device. And we did this offloading, really making sure that we don't give much room for the compiler to guess what we want. So whenever we offload the kernel, we really are explicit about which variables are private, which variables are shared and present on the device. And this helped a lot also with debugging. So then we use vanilla data directives for data movement, especially in the beginning of the time loop. We use ACC enter /exit data to move data in and out of the device. And then during the calculation, sometimes, of course, we need to have some syncing between host and device, and we just use very natural the ACC update cell for host and device directives. Then something that was quite useful, at least for me, is that always using default present when offloading finite difference kernels in a loop, because if I forget to move some data to the GPU and I have the default present when offloading the loop, then I get immediately a runtime error, which at least in the NVIDIA compiler will tell me which variables I sort of forgot to have on the GPU, so I can then go back and debug. And something that's also important is that so CaNS runs fully async on the same queue. This is not necessarily important for large 3D kernels, but for small 2D kernels, especially boundary condition, the latency associated with launching the kernel is actually much larger than the execution time. And so we have many 2D loops in this boundary condition. So what we should, and async also takes care of hindering this latency. So this was something that we could really see on the profiling timeline if we wouldn't have these small 2D loops with the async clause. And then there's some nice interoperability features and some tricks to avoid memory allocation and deallocation, which I will detail in the next slides. And often, so profiling was very important, not only the whole timeline, but then just taking, kernels that were representative of important parts of the solver, write small toy problems and play a bit with different versions of them before, optimizing the whole code. And yeah, so I found that profiling on the GPU with OpenACC Fortran was not really super straightforward. So I also wrote a small profiler with a, funny TikTok API like MATLAB. And maybe if it's useful to you too, you can have a look here in the repository. Okay, so now some examples. First, I just want to praise the really cool interoperability features of OpenACC with CUDA, QFFT, or with CUDA libraries at least. So when using the CUDA library, for instance, I had to pass to the library in to this actually subroutine CUDA malloc, CUDA Fortran device array or CUDA to allocate some device memory. And so that's what I did. I declared it with device attribute. So this is CUDA Fortran, and I call CUDA malloc with this or CUDA array. And then to interoperate with OpenACC, I allocate sort of the host array work. And then instead of using directives to move the data, I use from the runtime API this ACC map data, which tells the compiler, look, the corresponding device array associated with work has been already allocated, and it is this work CUDA array. So that's really allows for a really swift interoperability. And another important thing, because again, CaNS runs all, like the whole calculation is on the same queue, some parts of the algorithm call external libraries. And so to those external libraries, I was also passing the CUDA stream associated with Q1. And I can also fetch this with the ACC get CUDA stream from the ACC runtime library. So really neat. And now some tricks to avoid some common pattern in CPU Fortran code, at least in ours, that we, in a subroutine at times, we had an array that was declared with some statically with a certain size n. And if we do the porting of this naively, what happens is that during the calculation, we first allocate memory on the device, and then as soon as this array goes out of scope, so we exit the subroutine, as per the Fortran standard, the array will be deallocated. We don't want that. So one very easy 3 lines of code workaround is to allocate a workspace buffer array, which we did in the beginning of the calculation, stored in this module here, and then imported to the subroutine. Here it's actually with an alias called buff. And then instead of allocating the static array, we just have a pointer. We point to the workspace array, and then the whole code remains the same as the CPU version, excluding, of course, the derivatives for the GPU, the directives for the GPU offloading. Okay, so like summarizing this in a meme, if we have something like this in a CPU baseline we want to port, we should really avoid this because it will be deallocated when it goes out of scope. So we can replace this with a simple 3-line solution using a workspace buffer. So this is one trick that we employed. But of course, sometimes it's not really convenient to use these workspace buffers. So another way of overcoming this issue is using actually a feature that is intrinsic to the Fortran standard is the save attribute. So instead of declaring this static array, again, with size n, what we can also do, we can declare a dynamical array, allocatable attribute, and then add the save attribute. And in addition to other things, what the save attribute ensures is that this array will not be deallocated when it goes out of scope. So then the only thing I have to do is to write these small 4 lines, which make sure that this array is only allocated. So this is only executed the first time the subroutine is called, and it will allocate the array and move the data to the GPU. So again, this will avoid deallocation of data on the GPU, which is really a performance killer. So again, a really nice interplay between a Fortran standard feature and OpenACC. So I think this is what I wanted to say about these 4 lines of code. And yeah, so now we are really happy because after all this effort, we have reached a really highly performing Navier-Stokes solver, and we got computing time on the Leonardo, which is a Euro HPC flagship supercomputer, to perform simulations of turbulent channel flows at high Reynolds number, because there's still some outstanding questions about the nature of turbulence at very high Reynolds numbers that we still don't know. So this is a sort of a colorful fluid dynamics picture of a simulation with 90 billion grid points on Leonardo, which run on 256-800 GPUs. And I'm really excited to tell you that the wall clock per step per grid point is very small, about 4.9 nanoseconds on these N800 GPUs. So we are really thrilled with the performance that we were able to achieve. And with this, I come to the conclusions and outlook. So it was really my experience that OpenACC combines very well with Fortran standard features and interoperates really nicely with external libraries. So this allowed for a swift GPU porting while maintaining a sustainable code base and really without compromising performance. But during the development, the direct interaction between domain-specific, in this case, maybe myself, and GPU porting experts, mentors, was really key to achieve this performance. So we leverage some tricks when porting, which I just mentioned in the previous slides. And we are excited to be exploiting Leonardo to study turbulent flows at high Reynolds numbers. And all of this is open source. You are very welcome to try it too. And with this, I would like to thank you for your attention.